Mm. Hi guys. So today we're gonna explain various ways to estimate the diffusion coefficient in vapor and liquid binary mixtures. So first we're gonna talk about vapor and how to find its diffusion coefficient. So let's say in a binary mixture of species one and two, we would have to find the diffusion coefficient. We're gonna use this equation with 0.00266 times temperature with the power raised to 3.5. And then down denominator, we have pressure. We have now denominator, we have pressure times the molecular weight of the reduced or the blended molecular weight of species one and two times power half times the Lennard-Jones energy parameter collision parameter for species one and two raised to one half times the collision integral of one and two. And then so to find each of the individual variable, we can find um molecular weight of one and two, pressure and temperature from experimental data, or just any given data. And then we can find the um let me just write down as soon as Leonard Jones energy parameter. And then this one is collision integral. And then temperature, molar weight, and then pressure. And then diffusion coefficient. And then so we can find the Lennard-Jones energy parameter from ta data table. And then so for the collision integral, we can find collision integral through finding reduced temperature, which reduced temperature we can find through Lennard-Jones uh collision parameter of species A. It's epsilon, not E actually. So epsilon of A over K. So K is the Boltzmann constant with a value of 138 times 10 to the negative 23 joules over Kelvin. And then so we can find the Lennard-Jones parameter of A and B divided by Boltzmann constant to find the reduced temperature. And then we can therefore when we get the reduced temperature, we can use that value to use the table data using reduced temperature. And then so that's for vapor. And we can move on to liquid. So in liquid, we can use Stoke and Einstein equation. So Stoke and Einstein equation is gonna look like this. We have Bowman constant times temperature over 6 pi times mu times R. So KB is Bowman's constant with the value that I just mentioned. And then temperature, and then liquid viscosity, and then molecular radius. However, this equations only apply for diluted solution. So what about concentrated solution? How do we find it? So, however, what if you can't identify all of the variables? So like, what if you can't find R, or what if you don't know the viscosity? What's the other solution? So we're gonna use Vicness formula using infinite diluted s- solutions driving force. So like there would be diluted of 1 and 2, or diluted of 2 and 1 driving force. And so why do we use this? Because with this equation we can use interpolation. So notice this is not linear interpolation. This is logarithmic. So like similar idea to linear interpolation to find driving force of um the binary mixture at any component, mole fraction of any component. So the formula is gonna look like this. So we have the driving force of 1 and 2, or like the average, not average, but the blended driving force of binary mixture 1 and 2 is equal to the driving force, the infinite dilution of species 2 times x2, so times mole fraction of 2 plus the dilution, infinite dilution of species 2 in species 1 times x1. So now we get the driving force of binary mixture 1 and 2 through Vicness solution. So Vicness equation can also apply for any component or any mole fraction of x1 or 2, x1 or x2. So that's why it's more useful than the Stokes-Einstein equation, because it can only be applied for a diluted solution. So that's for part A. So moving on to part B, derive an equation of continuity of component A using a unidirectional system with rate of formation of RA. So we're gonna imagine a cube with a 3D cube with three direction dx, dy, and dz. And so you can have a total molar flux of Na species A coming in and the flux coming out, Na plus dz. So now we can define an energy balance or material balance for this. So we can have rate of formation. So Ra stands for volumetric rate of formation of species A. So as the molar flux goes through the cube or a certain surface, it's gonna generate or react to form some species of A. So we're gonna need to times it with the volume dx, dy, dz, and then we're gonna have the in minus out flux. So Na minus Na plus dz times by dx, dy, because times the surface area, dx, dy, is equal to the change of concentration of A with respect to time times dx dy. dx dy d times the change in concentration with respect to time times dx, dy, and dz. So now we can derive these equations, okay? So we can cancel out the x and dy. We have Ra d times dz over Na minus Na plus dz plus change in concentration of A with respect to times dz. And then we're gonna divide both sides with dz. So we have Ra times Na minus Na plus dz over dz equal to change in concentration with change in time. So we know that Na plus N over A plus under A plus dz is equal to Na plus dNa, change in the total flux of Na with respect to T with Z times dz. So when Na minus Na plus dz is equal to negative dNa dz. So now we plug it back in the equation. We have Ra minus the change in Na with respect to dz, because this cancel out, equal to change in concentration of A over change in T. And then now we just rearrange the sign so that change in the molar flux, total flux of A with respect to Z is positive. So we have dNa dz minus Ra plus change in concentration with change in time is equal to 0. So that's how we derive the equation of continuity. And then next, how equimolar counter diffusion arises at vapor-liquid interface when the enthalpy of vaporization is independent of composition. So now the question is asking, why is there the same amount of molar molar counter diffusion? So counter diffusion when happens when two two species diffuses in two in opposite direction. So essentially, both species diffuse each other against each other at the opposite direction. And why does that happen? So let's imagine a bubble, like a vapor bubble, and over here there's liquid, and then there's like an equilibrium interface over here, liquid vapor equilibrium. And so we have component Y1 and then we have component X1. So here's the explanation. So when in chemistry or in thermodynamics, chemistry, thermo, we learned that when a molecule turns goes from liquid to vapor, it's gonna absorbs energy or enthalpy of vaporization. And then so when that and then at the same time and at the same time when that vapor condenses into liquid, it would release release that same amount of enthalpy of vaporization. So essentially, if a molecule um absorbs all the heat of the enthalpy of vaporization turns to vapor, and then when it reaches this liquid interface, the equilibrium, it will condense back into liquid and releases all of that enthalpy of vaporization, and then that energy is going to be absorbed by the liquid molecule, which turns into air vapor. So they just uh essentially counter diffuse each other. Liquid turns into vapor, vapor turns into air. So let's write the equation for that. So we can have um when we write energy balance, we would have N to the YA times enthalpy of vaporization plus N to the XA or X1 times HVAP equal to 0. Assume adiabatic, no energy accumulation. We can have N, since A va H enthalpy of vaporization are the same, we can have NY1 is equal. Mole flux of vapor and mole flux of liquid are the same. So that's why they are equimolar. So solution when a molecules vaporize from liquid to vapor, it's gonna release same amount of energy. It's gonna absorb, I mean, it's gonna absorb as when liquid turns into vapor. For when vapor turns into liquid. Okay, so that's for number three, and then move on to number four. So we know that when a species A cattle on a cattle surface and make two total moles of species B, we know that the mole flux of species B in total would have this twice as moles, or not moles, but mass twice as amount as species A. So we can have species B in total. So since species A makes two species B, then one species B would be equal to two times of that molar flux of species A. And then we have that negative. So like right here, we have NB over 2. So B would be like total flux, total molar flux. When it divided by half, it's equal to the total molar flux of species A. So that's why 1A makes 2B. So yeah, we move 2 over here. We got 2Na. However, there's a negative because species A is being consumed, which triggers a negative sign, and then species B is being produced, making it positive. So when um the total molar flux Na plus Nb is equal to total molar flux, we have Nb is equal to 2Na, so we plug that in. Na minus 2Na equal to N, so we have the total flux is equal to negative molar flux of A. So that's we have for the first one. For the second one, where 3A makes 1B, we would have all three species of A in A. So like let's say A total would make 1B. So A would be species B divided by 3 to have the equal molar flux, total molar flux. And then don't forget the negative sign because B is being A is being consumed, but since we switched signs around, um, let's see. So for species 3A, that mixed B, we would have the entire species B would just be species A divided by 3 with a negative sign. And then when you do the total molar flux Na plus Nb equal to N, we plug Nb. So we have Na minus Na over 3 equal to N. So we would have 2 2/3 of Na is equal to total molar flux. So that's the relationship of what we have over here. Thank you for listening.